David Smith here with another Flip Classroom math video. A few tips before we start. Remember that you can slow down or speed up the playback if that helps you follow along. You can also pause the video at any point to catch up with your notes or to try the problems before I explain them. Finally, you could turn on the captions and read my words below on the bottom of your screen. Today's lesson covers using differential calculus, that is, first and second derivatives, to describe the motion of objects. This is a physics topic called kinematics, or the physics of motion. So we're going to use our calculus, our derivatives, to describe motion. So first we need some vocabulary to help us go through this material. Distance. That's the length of the path that an object has traveled. So that could be any kind of a path to go from A to B. Displacement is the difference between the ending point and a starting point, or a position, a current position, and another fixed position. So these two terms seem similar, but they definitely are different. So let's take a look. Here is my A and my B. The distance could be this path. You know, this is like a road going through the twisty mountains, getting from town A to town B. So the distance traveled will be whatever that length of that curvy line is. The displacement is how far away are you from A when you're at B. And that's a straight line. So in this lesson, we're going to talk about straight line motion almost exclusively. Okay, let's look at the calculus that relates three things in physics, in the physics of particles at motion. So we have our displacement function, that's position, where is the object? We have our velocity function, that's how fast is the object moving? And then finally we have our acceleration function, which is how quickly is it speeding up or slowing down. So let's take a look at how that works. First off, displacement is used S as a function of time. All of these are as a function of time. Velocity is V of t. Velocity as a function of time, and acceleration is A of t, acceleration as a function of time. Now here's the interesting thing, is that the velocity function is the derivative of the displacement function. This is the truth of it. This is out there. This is what Newton figured out when he was looking at the planets. So S of t, the derivative of the displacement function, is our velocity function, and that tells us our velocity. Finally, the same relationship holds for acceleration. So the acceleration function is really the derivative of the velocity function. Since velocity is the derivative of displacement, acceleration is the second derivative of displacement. And this makes sense in terms of rates of change. Okay, so if position is not changing, if it's constant, then their velocity would be zero because there's no rate of change here. So when you take the derivative, that tells you the rate of change. So if displacement is changing, then we have a function that when we take the first derivative of that, we can get the rate of that change, and that would be the velocity. So if I have an object whose displacement is changing, that is, it's moving, then when I take the derivative of that function, I'm going to get a velocity. That's the rate of the change in displacement. So if we bump that up a notch, if we say that the displacement is changing like at a faster and faster rate, that means that the velocity is changing. So we're going from 20 to 30 to 40 miles an hour. That means we have acceleration, and the rate of the increase in velocity is found by the second derivative of displacement, or the first derivative of velocity, and that would be the acceleration. So acceleration is the rate of change of velocity, and velocity is the rate of change of displacement. So these three functions are related together. In fact, if you have any one of them, you can find the other two. It's pretty cool stuff. So one other important point to see here, if the velocity and the acceleration have the same signs, then that means our object is accelerating. Okay, it's speeding up. If the velocity and the acceleration have different signs, then that means our object is slowing down or decelerating. Okay, let's take a look at a problem where all this comes into play. So here's where we start. We've got a particle and it moves on a horizontal line. Keyword, line. It means we're going in a straight line So we don't need to worry about distance because we're worrying about displacement, okay? So here's our displacement function, 5t squared minus t to the fourth in meters. So whatever t is, let's say seconds, I think that's what this one is, seconds. You plug your seconds in here and that tells you where the object is, how much displacement has occurred from its fixed starting point to whatever the ending point is. So here's our prompt. Find position, velocity, and acceleration at 1 second. So I've done that first one for you, position. So that would be just s of t with our displacement function. So we just take s of 1, plug it into the function, and we get 4 meters. So after 1 second, this object has gone 4 meters from its starting point. Great. Okay, now we need to find its velocity after 1 second. So I'll give you a prompt, but then I want you to do the rest. You need to find the derivative of the displacement function and then put 1 second into that to get the velocity. So pause the video, do that, and come back. Okay, so I took my first derivative. I just applied the power rule to both terms in there. And so this is my first derivative. This is the velocity as a function of time. Then I just plugged in 1 for my velocity, and I get 6 meters per second. So after 1 second, this object is going 6 meters a second. So now I'd like you to pause the video and do the same to find the acceleration at 1 second. Okay, here's how I did that. Here's my acceleration function, which is just the derivative of the velocity function here. So we get that. I'm just going to plug 1 into for t here. So I just have 10 minus 12 times 1 squared. I get minus 2 meters per second. So that would be my acceleration at 1 second. Now, I want you to, there's something we did on the last board that allows you to say one more thing here about our results. So maybe flip back in your notes, take a look at that, see what you think it is, and then come back. So what we're seeing here is the velocity is positive, the acceleration is negative, so the object is decelerating, it's slowing down. Now, you might be tempted to say, oh, well, but that's because it's negative, it's slowing down. Not quite true. There's a subtlety here that you have to realize. This object could have a negative velocity. All that would mean on the number line is that it's moving at a velocity to the left. And so if the velocity was negative and the acceleration is negative, it's actually accelerating in the negative direction. So really, for something to be slowing down, decelerating, these two signs have to be different. Okay, let's ask some more interesting things about our situation. So same scenario with our particle, and I just reproduced our displacement, our velocity, and our acceleration functions here from the last board. And so now here's a question that's kind of interesting. Find the value of t when the object is at rest. So we already know that the object has a velocity at 1 second and that it's decelerating, okay? So it's slowing down. So at some point, it's gonna be at rest, which means no velocity. Velocity equals 0. So that should be enough of a hint for you to find the times when that happens. Pause the video and see what you can come up with. Okay, here's a prompt. When the velocity is 0, this function is 0. So whatever t takes to make this thing 0 is gonna be your solution, your answer to this question. So I set you up here. Here's the velocity function. I set it equal to 0. Now go ahead and use your algebra skills to find the times where this thing is 0. So what I did is I just factored out a 2t from both those terms. Then I have this times this equals 0. So I just branch out. So 2t equals 0 gives me t equals 0. So that's one moment where this object is at rest. And that makes sense because basically, you put 0 in for t in our velocity function and you don't get any velocity. Now, in our acceleration function, that's not the case. We have this constant here, but we'll get to that in a minute. So that's one solution. The second solution is this binomial set equal to 0. So I just worked my algebra and I got all the way down to t equals root of 5 over 2. Now, technically, when I take the square root of both sides here, I have a minus value for that as well. So why am I taking that out? Think about that for a minute. So Generally speaking, with an experiment, with a situation where we deal with time, we don't deal with negative time. That's like before the situation starts to happen. So when we're dealing with time, we're almost always going to only deal with positive values of time. So we have two places where this object is at rest. We have 0 seconds and we have √5/2 seconds. I've summarized the most recent result we got on the last board. The object is at rest at time t equals 0 and time t equals √5/2, which, just for convenience sake, because we're going to throw this on a number line, that's about 1.58 seconds. Okay, so here's our next prompt. Find the values of t for when the object is speeding up and speeding down. So let's interpret this a little bit. Find the values. So we want to know all the t's for when it's speeding up and all the t's for when it's slowing down. So this is an interval type question. This is like when we were asked about derivatives, find the interval for when the function is increasing or decreasing, or the interval for which it is concave up or concave down. So this is basically that question in a physics context. So speeding up or slowing down. Here's the thinking for that, is that when it goes from speeding up to slowing down, it has a moment where there's no acceleration. So that's where this function is equal to 0. So what we have to do is set this equal to 0 and solve for t, and that will tell us when the function is neither accelerating or decelerating. So go ahead and do that and come on back. Okay, so what I did is I just set this one equal to 0. I factored the 2 out. So I have a 2 outside. That does not impact us because there's no variable here. So all we've got to do is figure out when this part is 0. So I went ahead and set that equal to 0. I moved my 6t squared over, divided through, took a square root, and I have square root of 5/6. So that's 0.913 seconds. So that's the point at which our particle goes from accelerating to decelerating. So now we need to answer this question. Find the values for when it's speeding up and speeding down. So remember, the key thing there is, are the signs of the velocity function and the acceleration function the same, or are they different? So think about that for a minute, see if you can take some steps, and I'll be right back. Okay, let me direct you to this spot over here. I set up my number line. These are my important intervals, okay? This is where the acceleration goes from accelerating to decelerating. This is where our object is at rest, and this is again where our object is at rest. So these two are the zeros of our velocity function, and that's the 0 of our acceleration function. So remember, those are the turning points for each of those functions, for where their signs change from positive to negative, or the signs of their derivatives do. So now what we need to do is we need to find out what the sign of velocity and acceleration are in each of these 3 intervals, and then that will tell us where our object is either speeding up or slowing down. So go ahead, pause the video, do some plugins, and see if you can populate the 6 signs there that are needed to answer this last question here. 5 to the 4th is tiny. Okay, so I did my math up here. I'm not going to go over it, but basically I just picked some numbers that were inside each of these 3 different intervals. I used the velocity and the acceleration function to calculate the values at those intervals, and then I wrote down my positives and my negatives for the value of the derivative, and I added them to the chart here. So now I know where my velocity function is positive, positive, negative, positive, negative, negative. So now you need to read this graph and tell us, when is the object accelerating and when is the object decelerating? Okay, so check this out. My signs are the same. I'm increasing its speed, which is acceleration. My signs are different, so I'm decreasing my speed, which is deceleration. And finally, again, my signs are the same, so I'm increasing speed with acceleration. So let's look at what's happening with respect to the particle. The particle's speed is positive to here, and then it's at rest, so no speed, and then the speed is negative. Okay, so it's the rate of displacement, the velocity, we have a positive velocity, then we have a negative velocity. We start with 0 velocity, so these are the two at-rest points. So we have a velocity that increases, a velocity that decreases, but it's still a positive velocity. And then we have this spot where where it goes at rest, and then the velocity is negative. Now, acceleration means that from here to here, this is the turning point of our second derivative, our velocity is increasing, now our velocity is decreasing. So the velocity is decreasing, but it's still positive. So that's why it's positive there. So this is where our acceleration is increasing, now our acceleration is decreasing. Finally here, the acceleration is at 0, and then the acceleration goes down, but our speed is going up because now they're both the same sign. Okay, one more step in this kind of long problem. Here are our results from the last things that we did. All of the stuff that we've got is right there for reference. So here is our question. How far does the object travel in the first 3 seconds? So how far is a distance, not a displacement question, okay? So we want to know the distance. Okay, so now this one is tricky because you have to conceptualize what's going on. The object travels in the positive direction first and then travels in the negative direction. So we're going to kind of tease that out here a little bit. So check this out. Okay, we need 3 displacements. We don't have a distance function, we only have a displacement function. So there's a very definite critical thinking step in using our calculations to figure out distance. So the 3 key points we need are, we need the starting time, t equals 0, and that's just 0. So our displacement at 0 seconds is just 0 meters. Now, the second one we need is 1.53. This is where the object is at rest after it's been increasing velocity for a while and then finally decreasing velocity until it hits that point where the velocity is 0, it's at rest. Then after that, our velocity is negative. So instead of going one direction, we're coming back the other way. Our velocity is negative. So this place is where the object is at rest. So I put that in the displacement function, and our displacement is at 6.22. So then I need to figure out what our displacement is at the end of our time period, which is 3 seconds. So I just put 3 into the displacement function, and that gives me minus 36. Now, it takes a little bit of thinking to figure out what to do with these numbers. So my way of coming to clarity uses a number line, and I think you'll see that it's pretty clear. So let's check that out. Okay, so over here, I've put my 0, let's label that. That's our starting point, no displacement, no distance traveled. And then at 1.53 seconds, this is where we're at rest again. Velocity has been increasing and then decreasing to the point where we're at rest. We've traveled 6.22 meters. Okay, so that's a first bit of distance. Now, at time 3 seconds, we have come back. Our displacement was 6.22 positive. Now our displacement is minus 36 negative. So our distance traveled is going to be from here to here, and then from here to there. So this would be 6.22 plus, now we have another 6.22 to get back to the 0.22, and then we have 36 from the 0 to here. So that would be another 36. So you add that together. When you add them together, you get 48.44 meters. That's the total distance traveled in the first 3 seconds. So again, to summarize, the critical thinking part in here is you have to separate out distance from displacement. We don't have a distance function. You can't plug in 3 seconds and have it tell you how far it's gone because the path it's taken is complicated. It first goes this way and then it goes that way. So we have a displacement function. So that lets us tell us where it is at certain points in time in terms of displacement. And then I found it easiest to use a number line here to just figure out what the distance is by adding the different segments on the number line. Now that you've finished, write down any questions so you can bring them to our next class and get some help. Remember that you can always watch the video again to improve your understanding. If you enjoyed it, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.